Welcome back, everyone. In today's session, we continue with section 1.3 on Malthusian population dynamics. In part 3, we're going to bring everything together by connecting the land market and the labor market, deriving the wage equation step by step, and understanding what happens to wages when land per worker changes. This part is all about intuition, how the rent of land interacts with productivity, and how the remaining income becomes wages, which is the crucial conclusion of this point, of this part of. And by the end of this video, the entire Malthusian mechanism will hopefully make complete sense. Starting with our production function, output depends on total factor productivity and land and labor. Because the function f is homogeneous, and because we've assumed constant returns to scale, therefore if I divide the whole function by n, the n will come inside the bracket because of these assumptions. Therefore, if I cross multiply now, I'll have aggregate output is equals to z multiplied by n, and now we have L and n power minus 1. Okay, at this point we know that the marginal product of land should be equals to the real cost of rental cost of land, which is x, and the marginal product of labor should be equals to the wage. And we've already discussed how these are because of diminishing returns, both these curves are negatively sloped. Okay, so let's first take the marginal product of land, which is the partial derivative of output with respect to land. And as you can see, land only comes inside this function, and therefore everything else is treated as a constant. So when I take the derivative, I'm going to be left with the derivative of this function with respect to L, and then the derivative of, basically I'm implying using the chain rule. Anyhow, so the n and n cancel out, and I have a z and then the derivative of L with respect to L. Okay, I think it's safe to write this like this. So the marginal product of land is equals to z and small f small l. So we have one equation, and we know that this is diminishing. So this has diminishing returns. So therefore we have a marginal product of land which looks like this, with x on the vertical axis and L on the land per labor on the horizontal axis, which shows that if there's a fall in the rental rate of land, then it makes it easier for people to buy and use more land, so land per worker rises. Okay, so we've done this expression. Now let's do the marginal product with respect of worker per worker. So let's do that. The production function is this. I'll just copy it down. And now I want to take the partial derivative with respect to n. Now n appears in two places. It appears over here and it appears over here. So therefore we'll have to use the product rule, which is that if y is a function of u and v, then the derivative is that you take turns. So you place u as it is and the derivative of v plus v as it is in the derivative of u. So let's do that here. I'm going to first just z is a constant, so it can just come outside. Okay, so n remains as it is, and I take the derivative of this function with respect to n. So I've done the derivative here because I've put the sign here, but I'll need to take the derivative of this expression as well, which is going to be minus L n minus 2. Okay, I'm done. Plus f at this expression as it is, and the derivative of n with respect to n is just a 1. So therefore I have a f L n minus 1. Okay, done. So therefore I have a z and n derivative. I can write a small l here, and actually, and it's being multiplied by let's just open this up actually. So this becomes multiplied by minus L n minus 1, because we have a 1 here, so a 1 minus the 2 is a minus 1. Okay, and then the derivative plus f L n minus 1. Okay, so this is basically small l. This is the derivative. This is a small l. This is again a small l. Okay. So we know the optimality conditions were, the optimality or tangency conditions gave us this, that the marginal product of land should be equals to x, and the marginal product of labor should be equals to w. So let's rewrite this expression and put the optimal conditions here. Okay, so we can write a w here, right? And what about this? So marginal product of land was equals to this, and therefore I can substitute it here. Let me open this expression up. Minus L Z F prime L plus Z F L, where we just found out that the marginal product of land is equals to a Z F derivative. So therefore I can write the marginal product of land in over here, right? And what is the marginal product of land equals to? It's equals to x. So I have an xl here. And what is this? This was the production function, but in what terms? In a per worker term. So this is actually a small y. We've already done this conversion, that small y is z f small l. So therefore it can be substituted like this. Okay, so this is a very interesting expression which says that w is equals to y minus lx. And what it means is that when the rent for land is paid, if this is paid out of your income, the remaining money goes into paying the workers. Okay, so what we can say is that when the rent for land is paid, the remaining income is paid as wages. Okay, and we should also be aware of the relationship between wages and land per worker. So the question could be, what is the relationship between wages and land per worker? So we're interested in the fact that if there's suppose a loss of population and it leads to higher land per worker, what impact will it have on wages? So suppose there's some kind of pandemic and it leads to a lot of the death toll increases. Sorry for sounding a bit morbid. And therefore, the number of workers available falls. And therefore, the people who are still alive with a constant supply of land, what happens for them is that the land per worker actually rises. So, what happens to the wages? Okay, we know that we already had this diagram for what will happen to wages when labor falls, because we have a labor demand curve, and we know that when labor falls because of whatever war, famine, any kind of increase in death toll, then it should lead to a fall in N, should lead to a rise in W. So we know that any fall in N should lead to a rise in W. So what we need to show then is that as a rise in land per labor should have a positive relationship with wage. So how can we show that? It's kind of it's not that difficult to show because we already have this expression over here. We can just take the derivative and prove the relationship. So for instance, we had wage should be equal to the marginal product and therefore equals to this. And I want to see the relationship between wages and land per worker. Constant remains there, and I'll have to apply the product rule here. So let's go on with that. Minus L as it is into the derivative of this function, so double derivative, and then the derivative of minus L, which is just a 1, and the first derivative as it is, plus this is the first function, so just the first derivative. As you can see that this cancels out, and then we have a minus ZL and the second derivative of L, which we know that the second derivative of L is actually negative due to diminishing returns to factor, which we've already which we've shown by showing that the production function actually looks like this. So the first derivative is always a positive, but since we are going to get like a maximum point, therefore the second derivative is going to be negative due to diminishing returns. So therefore, if this is a negative expression, this is positive, and we're multiplying it with the negative sign, we're going to have a expression which is greater than 0. So therefore, the mathematics also tells us that the relationship between wage and land per labor is greater than 0. So what does this mean? We also know that a rise in L is going to lead to a fall in X as previously encountered. So what does this mean? We had this expression over here, right? This, what does it mean? We have a law here then, that if land per labor is rising, and because of which X should fall, then the impact on X will outweigh the impact of L. And because it outweighs it, therefore, overall wage has to rise. So, putting all of this together, we can draw two diagrams side by side. One that shows the relationship between X and L, and we've just shown that when X falls, X actually falls due to a rise in L. So we can show it like this. X is falling because of a rise in L. This is the marginal product of land. And now we have actually a positive relationship between land per worker and wages, because we've just shown that when L rises, as a result, wages will rise. So it means that if there is some kind of loss in population, then people who are still alive are going to start making more money than before. And you can relate that actually to like unemployment, because if there's a loss in the labor force and there's a lot of people that were working before who are not working now, so the firms are in actually a weaker position. They need people to work for them, and they can't find that many people to work for them. So the bargaining power in this scenario is with the workers, and therefore they can demand higher wages because they are now the scarce source. Anything which is scarce can demand a higher price for its service. So this completes part 3. We've now linked land and labor, wages and output into one unified picture, which was this equation. And we've seen exactly why wages rise or fall as land per worker changes in a Malthusian economy. In the next section, we'll build on this foundation and move deeper into the supply side of the model of the economy. So the Malthusian model is actually complete. So that's all for this model. In the next video, I'm going to cover section 1.4. So take care for now.